All right, good morning, everyone. Sorry for the delay. There's some technical difficulties. All right, good morning. So, so the HDMI connector doesn't seem to be affecting the projector at all. But that's okay. I can use this. So, so one thing is I posted to Piazza a feedback form, so you can suggest improvements to the class or tell me what you're specifically interested in learning. And so sometimes, like if somebody's interested in a topic that's related to something I can present, I can try to steer it at least a little bit in that direction. And also, if a lot of people are interested in a particular topic that I wasn't planning to cover, then we can try to cover it. Okay, so today we're talking about edge detection. Last class we talked about how to use filters for matching and compression, image representation with pyramids, and texture and filter banks. I just wanted to review a couple things that I've gotten a lot of questions about. So one is creating a Gaussian Laplacian pyramid. So one thing to point out is that the last image of the Gaussian pyramid is the same as the last image of the Laplacian pyramid. So your Laplacian pyramid is L1, L2, L3 to Ln. Your Gaussian pyramid is G1, G2, G3 to Gn. And then when you create an image from the Laplacian pyramid, you start with, in this case, a 4-level pyramid. You start with L4, which is the same as G4, upsample and smooth it. Then when you add that to L3, it becomes exactly G3. And that's because L3 was defined as the difference between G3 and the upsample smoothed Ln. The reason to do smooth and upsample rather than to create the next level of the going back to here. The reason why we smooth and upsample, say, G2 and subtract that from G1 instead of just subtracting the smooth G1 from the original G1 is that it makes it so that the reconstruction will be lossless because of biconstruction. Okay. So another thing I forgot, so I think I said this was n log n last class. It's actually, I think, should be O of n plus m if you have two images where if you're trying to do coarse define alignment using two pyramids and you're just doing translation, then you've got to do downsampling to create the pyramids, which should be O of n plus m. Because if you're downsampling by a factor of 2 every time, then it'll be like O of n the first time you downsample, then O of n over 2, and O of n over 4. And so every time if you sum all of those up, it's still O of n. Also, the local neighborhood searches are just going to be O of m, where m is the smaller of the two images. So if you have two images of size n, it's actually just linear to do this coarse-defined search. Where if you search for a translation using Fourier transform, it'd be n log n. And if you did it using spatial filtering, it'd be O of n squared. So I also got this question a couple of classes ago, and I forgot that I actually have a figure for it. So the question was, why not just use an ideal filter? So the Gaussian has like that fall off with frequency. And the question was, why not just use a filter that selects a certain subset of frequencies and then use that filter? And the answer is that if you look at that filter in the spatial domain, it has infinite extent, which obviously we can't really represent. And so, so the effect of that is that if you apply that filter, you're essentially clipping it implicitly, and then it creates this ringing pattern. So this is like creating a circle, a filter that's like a circle centered at 0 in the frequency domain, and then applying it to this image. So you can also experiment with stuff like that on your own. And then I went through this stuff pretty quickly. I just wanted take a little bit more time on the bilateral filter because it's an interesting and useful filter. So to remove noise, it's common. The simplest thing you can do is use a Gaussian filter. A Gaussian filter takes a weighted average of all the nearby points, weighted by their distance to the center. So if you apply the Gaussian filter, it'll remove noise or like smooth the details, but it will also blur over edges, and often that's not desirable. You often want to keep your sharp edges sharp, but you want to get rid of noise due to imaging conditions or just smooth out the texture of some surface. So one of the best choices is called a bilateral filter, and it has these two terms here, the spatial term and the similarity term. The spatial term is the same as the Gaussian. It's just it's just weighting pixels by how close they are to the center. And the similarity is saying that if pixels in the local neighborhood are more similar in intensity to the center pixel, then they'll have more weight. And so as a result, when your filter is on the edge, like say you're just inside the red part of this example, then the blue pixels are not going to contribute much weight because they have very different intensities. So it's going to be some weighted average of the red pixels, and so you'll get rid of any noise that's present in the red pixels, but you won't smooth over the edge. So you can see a little bit in the original, it might be a little bit hard to see from where you are, but the blue pattern is actually kind of speckled in the original, while in the bilateral image, it's a nice smooth region. Oops, I've got so many computers here. All right, so today I mainly want to talk about detecting edges, which is a very important application in computer vision. It's used, has many purposes. So edges can come about from a variety of factors. You can have a surface normal discontinuity. So like when you're looking at the corner of a building, or in this example, the corner of the top of the bottle. You have the same material, but it's at two different orientations, and because it's facing the light source at different angles, you get a sharp boundary due to the sharp change in the surface normal. You can also have a depth discontinuity, so that's when you go from, when you hit the edge of one object and move on to the other, even if they were the same color, they'll be lit differently because they're in different parts of the scene, so you'll get a discontinuity. And often they're not the same color. So you often have edges that are due to a combination of different factors. You can also have a surface color discontinuity, like the lettering on the bottle, or an illumination discontinuity, like the edge of the shadow. So finding edges has many applications. One is that you might want to try to group pixels into objects or parts. For example, if you want to try to remove somebody from a picture, or you want to like recolor a particular part of the image in a graphics application. Or you might just want to know which pixels correspond to a particular object. Also, edges can be very good cues for 3D shapes. So one example is that we can usually interpret line drawings really well. So I'm sure you've seen line drawings before, and they make sense to us even though all they're telling us is some edge information. And they can also guide interactive image editing. So let me show you some examples of close-ups of edges, because our intuition about edges is usually not very good. So a lot of edges often seem really obvious to us because we're doing some long-range processing. So for example, like this is a very clear edge, as I'll show in the image domain. We also see this edge pretty easily, the edge between this little guardhouse and the palace behind it. But as I'll show, there's not really any edge there in terms of intensity. So this is a zoom in of that region. And so this edge is caused by a depth discontinuity. Or I can point over here now. This edge is caused by a surface normal discontinuity, and this edge is caused by also a depth discontinuity. But it has the benefit of having a lot more interior shadows, so it's much clearer. And then this edge is caused by also a depth discontinuity. This one is caused by surface markings or change of material. So edges caused by various reasons. So one way to characterize an edge in terms of the image intensity is that an edge is a place of rapid change of the intensity function. So if I plot along this line, I'll see that there's high values, and then it goes to low values, and then it goes to high values again. And often we'll encode this by looking at the derivative of the intensity. So where there's a peak in the derivative of the intensity, and that derivative has a large enough magnitude, we might say that we've detected an edge. So this is the intensity profile of a more natural image. So again, going along the red bar. And so some of the edges are really obvious. So you can see there's actually this part of the edge where you've got a sharp drop here corresponds to that surface discontinuity. And then the big drop down to almost black corresponds to where it goes from the inside part of the wall to the black wall behind it. It's not a black wall, but shadowed wall. Then this dot corresponds to this depth discontinuity on the left side of the guardhouse. And you can see that it's not really, you don't see much of a difference compared to other pixels that aren't on a boundary. So just to emphasize that, if now I take the gradient of this, the gradient is just the difference of neighboring values of a pixel. So it could be a filter that's like -1, 0, 1 if you're doing a horizontal gradient going across. So you can see like these sharp, this is the gradient, this is the boundary of the wall changing surface orientation. This is the depth boundary where you go from the inside part of the wall to the shadow. And then you hit the other wall. Then this is going from the shadow to this part of the wall of the guardhouse. So those gradients are really obvious. Those edges will be easily detected. But this edge is not very clear at all. Right? It has about the same gradient as anything else that's smooth. And then to make it worse, that was just an image. That was the image that I took. If I add a little bit of noise, say it's lower light conditions, now the gradients become even harder to find. Right? Now only the strongest edges really stand out. So even small amounts of noise can mess with your derivative function. So if I look at just this, it seems obvious to us where the edge is. But if I just compute a local gradient, then actually I've got about the same derivative everywhere. Because even though this has a long change over a scale of 50 pixels, or 50 units, whatever the x-axis is, the derivative is actually changing pretty quickly along that slope. So the difficulty is that difference filters respond strongly to noise. Image noise looks, so if you have a smooth region with some noise, or you actually have a true boundary, they're both going to have high gradients. And if you have a lot of noise, it's going to really overwhelm the gradient. So what's one thing that we could do about this? Right, so we can smooth the image, get rid of the high frequencies, apply some low-pass filter. So those are those are answers that people are giving. It's all the same. So we have to smooth first. So if we take if we take this example, and then we apply a smoothing filter, then we get this nice smooth function. The sharp noise, there are a variety of seats open if somebody wants one. And then we take the derivative of that smoothed function, and now we get a nice single peak in the right location. So we can modify our previous version. So instead of just taking the derivative, we want to find edges, we want to find peaks in the derivative of a smoothing function, or a derivative of the smoothed image. And fortunately, because the derivative of a convolution, because differentiation is also, you can operationalize it as a convolution. And convolution is associative. We don't have to necessarily run a smoothing filter and then run a differencing filter. We can just run a difference of smooth filter. So we can just, instead of running two filters, we can just run this one difference of Gaussian filter, and then it will give the same response as if we had smoothed and then run the differencing filter. So you can create a difference of Gaussian filter just by taking a Gaussian filter and then filtering it with 1, 0, -1. One question, just going back to the definition of separable. Is this a separable filter or not? Yes, right. Somebody said yes. So remember that a Gaussian is separable. So the difference of Gaussian will also be separable, because this is just going to be, if you separated this out into a filter in the x direction and a filter in the y direction, then you could just filter your x direction filter with this. So the difference of Gaussian can be applied very efficiently. So there's a trade-off between smoothing and localization. So the more you smooth, the more you remove noise, but you also blur the edge. And so if you use wider difference of Gaussian filters, you'll also find larger scale edges. With a very small difference of Gaussian filter, by which I mean you have a smoothing function with a small sigma followed by a derivative, you're going to find like finer edges in an image. If you have a very big sigma to your Gaussian function, then it's going to be a much longer scale derivative, and so it's going to respond strongly to larger edges, where thin edges will just get smoothed over. All right, so now if we want to use this to design an edge detector, what kind of criteria do we want our edge detector to have? So one is that we want it to have good detection, meaning we want to find all the real edges, and we want to ignore noise and other artifacts that we don't really consider to be meaningful edges. Could be like microtexture as well, like the little like dots on this wall. Probably we don't really want our edge detector to respond to them, ideally. Good localization, so we want to detect the edges as close as possible to the true edges, and ideally return only 1 point for each true edge. And so what cues do we have to do this? One is that we can look at differences of color, intensity, or texture across the boundary. So far we've talked about just intensity. Color is very similar. If you have two very different colors but the same intensity, you still might find an edge. And texture, like if you were looking at some, I don't know, some piece of marble where suddenly the marble like goes from being flat to upright, then by looking at the texture, you might be able to detect that change. And then there's also longer range cues like continuity and closure. Question?
What is return 1 point only for each true edge point?
So I guess that I can illustrate it a little bit later, but what I mean is that, let's go back to let's go back to this. Okay, so let's say that that we threshold this for like very high and low values. Then we're going to get these thick strips where we've got a high derivative, but often we just want a single contour. So we really want to know like what's the peak rather than having like bands where there's a lot of edginess. The question, to repeat it, is what do I mean by returning only a single point for a true edge? So there's also continuity and closure. So continuity means that that you tend to have like long edges, not just like little bits of edge. And closure is that an object should be there should be an edge that goes all the way around an object. So good edges often form loops. And then also we could apply high-level knowledge. So if we can recognize something, then we can use our information about that object to better find its edges. So in the case of the guardhouse, we're using things like like continuity and our knowledge of the shape of the guardhouse to help interpret the edge. It's not, as people, we're not just purely using local cues. So, one very famous and often used detector that encodes some of these principles is the Canny edge detector. So it's probably the most widely used edge detector in computer vision, perhaps even still. And the theoretical model is that you have some step edges, which means that you have intensity down here, it jumps up, and then higher intensity. That's corrupted by some Gaussian additive noise, meaning you added some random values to it. And Canny showed that the first derivative of the Gaussian closely approximates the operator that maximizes the product of signal-to-noise ratio and localization. So in other words, if you have like these step edges with Gaussian noise, then using a derivative of Gaussian filter is a good thing to do. So I'll explain the algorithm now. So as this example, we use this Lena image, which was often used. It's kind of a classic image for edge detection because it's got like this weird feathery texture and various, it's got like many different kinds of edges, curved edges, straight edges, very fine edges, coarse edges, so it's kind of a nice example for edge detection. So, all right, and then this is showing the derivative of Gaussian filters. So we've got one here in the x direction and one in the y direction. This is showing a 3D plot. This is showing an intensity, a scaled intensity image of the filter. So here I've taken the image, and this is the x derivative of Gaussian displayed using ImageSC without any other parameters. This is the y derivative of Gaussian. So this is finding vertical edges, changes in the x direction. So you can see it's like strongest on this vertical edge of the hat. And the y derivative will be strongest on horizontal edges. So it's like strong on our shoulder here and this brim, part of the brim of the hat where it's closer to horizontal. Then we can compute a gradient magnitude, which is just this image squared. By squared, I mean pointwise squared. So if I call this x and this y, this is x dot hat 2 is in MATLAB notation. So that's all the elements of this squared, and then plus all the elements of this squared, square root. So it's the gradient magnitude. So here the bright values are 1, the dark values are 0. Or actually, I think it's also rescaled according to the max magnitude just for visualization purposes. All right. And then second, I can get the orientation at each pixel. So I think it's actually probably worth going to my weird document camera here. Okay. So, well, this is... Oh, okay, that works. All right, so basically we have a gradient in the x direction. So I'll call that gx. That's the response of the x gradient filter. And then at the same pixel, I've got some gradient in the y direction. So I can concatenate those together. So I can think of it as I've got an x gradient here, and then going from that point, I've got a y gradient. And so this is my gradient vector. Let me see if I can zoom in. Ooh, that did something. Wasn't what I wanted, but it's fine. Okay. So let me just write it a little bit bigger. All right, so I've got my gradient in the x direction, gradient in the y direction, and my overall gradient. Right, and then the magnitude, the length of this, is the square root of gx squared plus gy squared. And the angle of the gradient is the arctangent of gy over gx. Or if I want to if I want to have a sign direction, which would also tell me, like, is it going from black to white or white to black, I could do arctan 2. So from just, so the important thing to remember is that only from only computing a gradient in the x direction and a gradient in the y direction, I can estimate the orientation of an angle, even if it's not exactly in the vertical or horizontal direction, and I can compute its gradient magnitude. And actually, if I use lots of oriented, if I were to use all derivative of Gaussians in all directions with that same, like, anisotropic or isotropic, the same round Gaussian, then I would still get the same information that I get just from computing those two gradients. Back to system PC. Let me just, that's fine. Oh, I forgot. So one thing I didn't, so here it's negative gy, and that's because in the image, y here means the row of the image, and it heads downward. So if you want your angle to be, if you want like theta to move this way, then you want to use arctan 2 of negative gy gx. Then you can use, then you do non-maximum suppression for each orientation. So far here, these edges are actually kind of thick. And so here the gradient magnitude is in the intensity channel, and the orientation is displayed in the hue channel. So I did a HSV representation that I converted to RGB. That's how I created that image. So now we've got a bunch of edges that if I were to zoom in on them would look like this. And we want to find the peak of those edges. So this is called non-maximum suppression. You want to find the pixel that's larger than its neighbors. And in particular, we want to find the pixel that's largest as we make cuts across the direction perpendicular to the gradient. So there's a pretty easy way to do this in this case. We say for every pixel, these dots that are equally spaced represent the pixel coordinates. And at each of these pixel coordinates, we've computed some orientation through the arctan of gy and gx, the gradient in the y and x direction. So, so you compute the positions of along the neighboring rows or, these are rows. Along the neighboring rows or columns, depending on the angle, of points along that direction perpendicular to the gradient. So here, the gradient is going this way, so we compute this position, which will have a floating point value in the x direction and be an integer in the y direction, and this value, which similarly has a floating point value in the x direction. It falls between these two pixels, and an integer in the y direction. Then I can interpolate to get these values. So R is the weighted average of these two gradient values, gradient magnitudes, where the weight is higher if R is close to, the weight for this pixel is higher if R is closer to it. And same for P. Then if the value at Q is greater than the value at P and greater than the value at R, then Q is a maximum, and I keep it. Otherwise, I throw it out. I set it to 0. So this is a good point to clarify what I mean by interpolation, which has been mentioned a couple of times. This is something called, one of the more common forms of interpolation is called bilinear interpolation, which means that I'm interpolating linearly in the x direction and then interpolating linearly in the y direction. And because it's linear, it doesn't matter which order I do it. So for example, suppose that I want to know this pixel value at location P. And these Qs are pixels on they're like the exact value coordinates of pixels on my image. So I have values at 91 to 10, 162, 95 at each of these 4 red dots. And I want to interpolate or solve for the value of a new pixel that falls in between the pixels whose values I know. So you can first interpolate in the x direction. So for each of these, let's say that P here is is halfway between these two pixels, and it's 20% down between these two pixels. So interpolating from Q1 to Q2 would be Q1 times 1/2 plus Q2 times 1/2, which is 150.5. Interpolating between these two values, halfway between, is, again, their average, 128.5. And then I can interpolate in the y direction. So since it's closer to the top than the bottom, I have 80% of the weight from this value and 20% of the weight from this value. So you want more weight the closer you are to a pixel. And then I can just write this simply as a bilinear matrix operation. So I have here 1 minus x, and x would be floating like numbers between 0 and 1. So this would be 0.5, 0.5, and this would be 0.8, 0.2, because I'm 0.2 down and 0.5 across from the upper left pixel. And then these are the 4 values of the surrounding pixels. And then this will give me my interpolated pixel value. So that's bilinear interpolation. We're doing actually just a linear interpolation here because we're just falling between 2 pixels on a row. And then this is getting slightly tangential, but it's a good point to mention the different types of interpolation. So this is bilinear interpolation. So points closest to this pixel that's blue are going to be blue. Points that are really close to that pixel that's red are going to be red, and in between, it's in between. There's also nearest interpolation, which I mentioned in the last class. That's where you just copy a pixel multiple times. So this is upsampling an image, doing nearest interpolation. It looks very blocky. And this is using bicubic interpolation, which actually I think is the default for MATLAB. And that will do interpolation using values from a larger area using a nonlinear function. So this is often, it's the slowest method, and it can be good for interpolating natural images that you want to display because it does a nice smooth interpolation. But one downside of bicubic interpolation is that even if the original image values are within 0 to 1, after bicubic interpolation, the interpolated values may go outside of 0 to 1 because it's a nonlinear interpolation. So sometimes, and that can sometimes cause an error or be something you don't want to happen. By linear interpolation, you guarantee that the values will always be between the values that are observed, and it's very fast. And nearest interpolation can be good for its simplicity, and in different cases you might want to use different ones. It depends what you're trying to do. But usually, if you're trying to upsample an image and you want it to still look like an image, you would either do bilinear or bicubic interpolation if you want it to look natural. Nearest will create edges between the blocks. And then to do interpolation with MATLAB, you can just do IM resize. If you're just resizing an image, there's also interp2. Right, so before non-max suppression, we have this image here. And after non-max suppression, we have this one here. And if you look at the slides on your laptop, it'll be sharper because the projector has lower resolution and not the same dynamic range as a laptop display. But you can still see that this is blur. This is like thick lines, and these are thin lines. All the edges are 1 pixel thick. And it detects the edges along the shoulder and along the feathery, whatever that is, feathery thing, feathery feather. So the final step is called hysteresis thresholding. So sometimes you might get some edges that are very strong, like along the shoulder, and other edges that are very weak, that might be on the inside of the face or just in the background. And some of those weak edges might be due to noise or due to texture that you don't really want to model. But some of it might just be bridging discontinuities in the sharper edges. So the idea of hysteresis thresholding is that you threshold. A threshold means that you say, check to see if the values are greater than some number. At two levels. You have a high threshold and a low threshold. So if a pixel passes the high threshold, then we call it a strong edge. If it passes the weak threshold but not the strong threshold, we call it a weak edge. And then if a weak pixel is attached to a strong pixel, then we keep it. Otherwise, we throw it out. So the effect is that all these edges in here will be discarded because they're weak edges. So here the weaker edges are shown as lighter gray, and strong edges are white. So these weak edges will be discarded. Well, if you look closely on this line, there's like strong, and then some weak, and then strong, and then some weak. That entire line will be preserved because you've got weak edges connected to strong edges. So compared to just thresholding, you get better continuity of your lines, and you also get rid of isolated little edges that that don't have strong gradients, and so they probably correspond. They may correspond to noise or to more minor artifacts. So this is just illustrating that same point. So here we would say these pixels, which have a lower magnitude, they pass the weak threshold but not the strong one, would be included in the edge because they're connecting to stronger pixels. And so this is the final result from Canny. So it's a pretty simple algorithm, but it's very effective, very fast. Tends to find a lot of edges that we don't care about, but it also finds the edges that we do care about, and they're localized really well. So another way of saying that, it's a high recall, low precision detector. So it's got, often we wouldn't, it depends what you're trying to do, but often we would say, like if you asked a person to draw the edges in the image, they might not draw edges among the feather, but they would draw them on the edge of the hat and maybe between these, for these boundaries. And Canny finds most of the boundaries that we care about as well as some that we don't. So to summarize the Canny edge detector, we filter the image with the x and y derivative of Gaussian filters, compute the magnitude and orientation of the gradient, just element-wise square sum square root to do the magnitude and atan for the orientation, do non-maximum suppression, threshold and length. So we define these two thresholds, the low and high thresholds, and then we do connected components and throw out any connected components that are purely formed with weak pixels. And so in MATLAB, this is implemented with just edge image Canny. And you can edit, you can look at the code. So you can edit edge, and then you can see how it's implemented. I think it's worth doing. It's not very complicated. So to get a really clear idea, I recommend doing that. So depending on the size of your Gaussian filter for the derivative of Gaussian, you can either detect fine edges or wider edges. So with sigma equals 1, you get all these fine edges of the stripes of this wallpaper. Where sigma equals 2, a lot of those edges disappear. You're getting more of the large edges. Another thing to notice is that with a larger Gaussian, corners get smoothed out more. So like this corner gets more rounded with a larger sigma. This corner of the mirror, you can see with the large sigma, it becomes kind of like a very round corner because the smoothing operator will just get rid of, it'll lose that sharpness, so the peak will actually round out. Right. I'm also going to show you some alternative methods. So Canny is, I think it was 83. It's pretty old, but still widely used. And then there's a lot of newer methods that are also worth knowing that tend to do better in terms of perceptual edges. So one is, these methods are often evaluated and sometimes trained based on an edge data set, the most popular one being the Berkeley segmentation data set, or BSDS. So here, this data set was collected by, they collected a set of images There's two versions, BSDS 300 and 500, that have 300 and 500 images, respectively. So then they asked 9 people to segment the image. So segment means divide it into different regions. And then they took the boundaries of those regions as the edges. And 9 different people are doing it for each image, so then they can basically average those edge images to get the probability that somebody would say that a pixel is an edge. And that's used for scoring. And so you can see here the segmentation, and on the right is shown a gradient magnitude image. So obviously gradient magnitudes by themselves don't always do a great job of finding the edges. One detector, or one of the most, another classic detector, I guess I could say, is called PB, probability boundary, that in addition to using intensity information, which is all that Canny uses, it also can use color and texture information. So the idea is that for every pixel, you look at the difference of brightness, the difference of color. So this is in LAB space. The intensity or brightness is the luminance channel, and then the color is the A star, B star channels. You look at the difference of texture histograms across the boundary, the difference of brightness, and the difference of color histograms across the boundary. And then based on all of those differences, you say whether there's an edge or not. So here's some examples. So here it's plotting the intensity, the what is B? Brightness. Oh wait, what is? Sorry, I'm forgetting something. Oh, I think this is just B is just the gradient of intensity. So here's the intensity. Here's the brightness gradient. So like the change in intensity. Here's the change in color, and here's the change in texture. So here you can see some examples of non-boundaries where it's just like in the middle of possibly a textured region or just a more smooth region. So here it's like smooth everywhere. Here you get some sharp changes of color and brightness, but not much texture. Here you don't get much change of anything. Then if we look at the true boundaries, here we've got a strong change in brightness. Here we've got a strong change in brightness and color. Here we've got a strong texture. Here we've got a strong change in color and texture. And here we've got a strong change in texture. So it's using more than just local brightness changes. It's also using changes of color and texture. And then it basically linearly combines these different gradients that are computed.
How do you measure the change in texture?
So the change in texture is, so first we compute something called textons, which is, in the last class I mentioned that one representation of texture is that you run filters of different like edge and bar filters over the image. And then you take all the responses at a single pixel and you cluster them, meaning that you assign them to quantized values, for example, using k-means clustering, if you're familiar with that. So you get a set of numbers for the textures that appear within a region. From that, you can count how many times you see each of those numbers. You compute a local histogram, and you compare those histograms on this side of the boundary to this side of the boundary. I think they use chi-squared distance. So that's kind of, might be many new terms, but you may be familiar with some of those terms. So basically, you're computing a descriptor per pixel of the texture. Then you're accumulating that descriptor across this hemisphere and separately across this hemisphere, and then comparing those accumulated descriptors to each other. And that gives you the difference. So here we can see the image, the brightness gradient, color gradient, texture gradient, and combined. And so using the combination, by far the brightness gradient is the most useful, but the combination of these gives you a better result than any one channel by itself. And then these can, it's worth spending some time looking at them, but us all looking at them at the same time is maybe not so worthwhile. So yeah, so some example results. So here you can see a case where PB does really well. It's actually pretty easy because this edge is obviously really easy, the white against the dark. And then it also does a fairly good job of finding the wolf edge, but one thing you can note is that it's missing the boundaries at the edge, at the legs. And that's because it's using these like larger areas to compute some of the differences. And those large areas will include like the snow on either side of the leg. So also it's using a larger difference of intensity filter. So while a human sees this leg quite easily, the PB detector is actually missing it. Here's another one. This is really relatively easy because you've got the bird and the branch against the sky. So it finds that exterior boundary really well. So a person might also label the interior of the wings, although it's not as prominent. And actually, PB detects those interiors as well pretty well. So this number, by the way, this is called the human score. This is the human score. So this is how consistent humans are with each other when they label the image. And this is how consistent the PB algorithm is with the humans. So a higher number is better. Now this is one where it really does poorly. It finds the edges along the horizon, but it doesn't find the edges along the long, thin giraffe legs for a similar reason to the wolf legs. It's not really good at finding edges of thin structures. And also, I mean, giraffes are kind of camouflaged, so it's not an easy, they're not easy to detect based on color or brightness or even texture very much among the legs. We can detect it more easily because we can find this really easily, and then we know it's a giraffe, and so we can infer very accurately the location of all the other important ingredients. Whoops, that's the wrong way. And then here's another example where it does even worse. So again, tigers are camouflaged, so they're a difficult case. But we recognize the tiger and use that information to help us. So people reliably annotate the edges of the trees, even though this tree isn't super visible, and the boundaries of the tiger. And they don't label the stripes inside the tiger. While the PB algorithm finds a lot of the stripes because they are significant color and intensity changes. And it doesn't find some of the important boundaries on the edges of the tiger because those changes really aren't very big compared to the changes within the tiger. So PB does poorly in that case. So I also want to make you aware of some other recent methods. So this is kind of the pattern of the way I will often present things, by the way. So I'll often spend a lot of time on the fundamentals and on the approaches that are kind of the foundation of all the more recent approaches. And then also try to point you to some of the latest techniques that are useful, but often they sometimes achieve much better results, but they're still relying on those fundamentals that we spent more time on. All right, so this is a machine learning method for predicting edges. It's called edge detection with structured random forests. I don't want to get too much into the machine learning method, but the basic idea is that you can learn to predict edges from training data. So you have some images with known boundaries in your training data, and then you want to predict for a new test image where the boundaries are. And so they want to learn to say, looking at a patch around a pixel, is this an edge pixel or not? And they also want to say that you don't really want to compute this independently for every pixel because then you'll end up with kind of like a little bit of a blurry mess of predicted edges. You want some kind of coherence in your prediction. And so they use something called a structured random forest. So what they do is they train this random forest, which is a set of decision trees that splits the data into different patches that have similar boundaries. And then, so this is an example of a patch that's drawn from some image and the ground truth boundaries. So then, depending on your features, you'll fall into some portion of the tree that will correspond to a bunch of boundaries that are similar to each other. You average those boundaries, and that gives you your edge prediction. So in particular, the algorithm works by extracting overlapping 32 by 32 patches at 3 scales. And the features are just the pixel values and pairwise differences in feature maps, where it's using LUV. It's a color space. You can think of it like YCRCB. So you've got a luminance channel and 2 chrominance channels. And you look at the color, the gradient magnitude, and the oriented gradient. And then just by the features are just the individual values and then differences of feature values within that 32 by 32 patch. Then you train these random forests, which are a general machine learning approach for regression or classification that maps from a feature to a label, to predict T-boundary maps, where you have T-trees in the center region. So you look at this whole 32 by 32 region, but then you just predict an edge in the center of it. So here's the prediction. And then you average the predictions for every pixel across all the patches, and then you get your final predictions. Because the random forest is very quick to compute which part of the tree each patch falls into, this method is really fast. So it runs at 60 hertz, where PB, the other method I showed you, takes a couple minutes because it's slow to compute these texture responses and histograms of texture responses. And it's also, it also performs similarly, if not a little bit better, on images in the test set. So just one second. So comparing the performance, this is getting, here higher is better. So PB, I skipped global PB as an extension of PB where they try to do better about enforcing continuity through spectral clustering. I decided not to get too much into that because we'll get into spectral clustering later in the class. But you can see that it's doing as well or better than PB, and it's also super fast. SC is the structured edge method. And another advantage is that you can apply it to things that are not natural images or not RGB images. So here they can retrain it on depth images, and it does really well at detecting edges in RGBD, which means RGB plus depth, like what you get from a Kinect camera for indoor scenes. So it's something that you can broadly apply as long as you have some ground truth to train on. Question?
What is how do you input the space information into the decision tree?
So the question is, how do you input the spatial information into the decision tree? One thing is that it's only making a prediction for this patch. The decision tree, when it's making predictions about this patch, is only looking at this patch, and it doesn't really know where in the image it came from. So one part of it is that after you make this prediction, then you know where you drew the patch from, so you can put it back into the image. But then the spatial information with this within the patch is encoded by that you would have a different feature for every possible position. So for every intensity in this, you may have one feature. So that's 1024 features will be intensities at each position. And then for every pair of positions, you could also have a difference of intensity feature. So 1,000,000 possible features from that. So you can have many, many, many features that are based on sampling intensities or differences of intensities or differences of color at each pixel or pair of pixels. So the nice thing is, so in the training phase, you might sample a large number. But in testing phase, you only have to compute the features that are used by the tree, which will be a much smaller number. And because it's a tree, you typically only have to sample on the order of tens of features, so it's very fast. So the whole thing runs at like 9 to 60 frames per second. So to repeat the question was, how long does it take to compute those features? I repeat the question. Well, I assume people in the back benefit from repeating the question, but also anybody watching the video, it's really important because otherwise people watching the video usually will not hear what any of you say directly. So, so here's some example of the edge detection. So this is the ground truth, and then this is multi-scale edge detection. It's detecting somewhat blurry edges, which isn't really penalized much in that measure. But one way that you can go from this to cleaner edges is just to take a canny edge map and then say that you're gonna take these values along the edges that are found by the canny edge map. So then this is suppressing a lot of the extra boundaries that you'd find in the canny map while giving you the sharpness that a canny map can produce. Question?
What does multi-scale mean?
Multi-scale, it means that it's computing edges at 3 different resolutions of the image. So you can think of it as it computes edges over the full resolution and then downsamples the image and then computes edges and then does it again. Often that can be helpful to get both like fine. So here you can see that it's getting like the thinner legs of the wolf are detected well. So at high resolutions, you might find those edges, where at coarser resolutions, you might find edges that correspond to larger scale changes. And then I want to just briefly mention a couple other approaches. This one I like because it's so simple. It doesn't involve any machine learning. And the idea is that, so if this is a motivating example. So this is kind of a hard image for detectors because you've got strong stripes in the zebra, but we don't usually consider those to be important boundaries, where the difference between the zebra and the background might actually be less than the difference between the stripes within the zebra. So this is plotting the luminance of pairs of pixels, and the idea is that if you see common differences that are commonly observed in the image are less likely to be edges than differences that are rarely observed in the edges, because most pixels are not edges. So in this case, difference from strong black to strong white, which is this area here, is actually much more common than these smaller differences. So here, the diagonal means that a pair of pixels has the same intensity. This means that one pixel was very bright and the other one was very dark. And this means that both pixels were somewhat bright, but they had slightly different intensities. So this actually, these colored circles correspond. So this green circle is going from the zebra's belly to the grass. And it's actually a small difference of intensity, but one that doesn't occur very often. That pair of intensities doesn't occur near each other very often. Where this red is the stripe within the zebra, but that bright to black actually happens a lot more often than this change does. And then this is in the grass, the blue pixel, the blue circle, and that's an area that happens really often. So as a result, you would find this underbelly pixel as an edge, but not the red pixel or the blue pixel. And so all they do is they sample lots of pairs of pixels, do something called kernel density estimation, which is just estimating the probability of a pair of pixel values based on some local neighborhood of that feature pair. And that's the affinity. And then for every pair of pixels in a local neighborhood, they look up that probability. And then they do spectral clustering, which is just a way of trying to separate different pixels, trying to separate pixels that are not similar to each other or that have low affinity. So it's a graph-based. You can think of these similarities as you can construct a graph where the nodes are pixels and you have edges between pairs of pixels that says how similar they are. As I said, we'll get into spectral clustering later. That's not the point right now. But I just like this because it just has a very simple intuition that if you see a particular pair of pixels very often, it's probably not an edge. But if you see a pair of pixels that don't occur near each other very often, then it probably is an edge. And this method generates very good results on the same quality of results as structured edge prediction. And then the last edge detector that I'll mention is a deep net-based detector. We'll get into deep nets later, so I don't want to get too much into the details. But the idea is that the deep network is essentially a set of compositional filters with nonlinearities between them. So you have, as you go through the network, you get coarser and coarser spatial predictions, but with information from a larger area of the original image. So this method makes, it has like a very detailed edge prediction, but one that's not very selective. And then as you get further and further in the network, you're dealing with coarser or higher spatial extents with lower localization. And so you tend to predict more of the important object boundaries, but your localization isn't very good. So it creates a set of edge predictions at different scales, and then it linearly combines those. And it learns how to combine them and produce all of these individual predictions based on training data. And this method actually does quite a bit better than the other methods that I presented. So human performance on this data set is 0.8. It's not too important to explain exactly what that means, but it's how humans have a consistency with each other of 0.8. This algorithm is 0.78 consistent with humans. And the other methods that I talked about are 0.74. So it's getting rid of like 2/3 of the error of the other methods. However, well, I don't have, you'll have to look at the paper to see examples of results. But even these methods that achieve very high quantitative accuracy still don't have really the same ability to predict edges or regions that people have. And one significant problem is that even once you have that predicted soft edge map, it's hard to break the image into different regions that correspond to different objects, which is often something that we care about. So local edge detection works really well. If you look at a 32 by 32 patch, if a person looks at that patch by themselves and a computer algorithm looks at that patch by itself, the computer algorithm is just about as good as the person at saying whether it's an edge or not. But looking at the whole image, where you have more context, people are still better because we can incorporate higher level information more better than the computer can. Question?
So do any of the state-of-the-art edge detection methods use depth information? Because none of these methods will still be able to detect the depth density edges as it's seen in the beginning of the picture.
Yeah, that's a good question. So the question is, do any of these methods use depth information? So there's a couple ways to answer that. So one is if you're just looking at an RGB image, none of the methods really have any explicit notion of geometry. So they don't use depth information in that sense. And you can view it. So if your goal is to do like a more complete scene understanding where you want to try to infer geometry and object labels and find edges, then you kind of need to somehow figure out how those things correspond to each other. So if you can find a depth discontinuity, then that means that you have an edge. If you find an edge, then you may or may not have a depth discontinuity. The other way to answer the question is, if you already have depth information, then these learning-based approaches can use it. So this example is where you have a depth image in addition to an RGB image. And then the depth image can be used to help predict the edges. However, one thing that's not, so my intuition, I've done work on many different things. And one thing I did once was doing segmentation of depth images. And my intuition was that depth would help a lot. But actually, depth doesn't usually help that much. And part of the reason is that it depends on your scene, but often you've got objects that are pretty close to each other, so they don't have much depth discontinuity, but they still have edges between them. And in particular, like if I put my hand against the wall, there's no depth discontinuity here, but there's still a boundary. Or if you have like a picture of objects on a table, everywhere they make contact, there's no depth discontinuity. So the absence of depth discontinuity doesn't mean there's not an edge. And often it's also a little bit more difficult to estimate depth near the boundaries, so you end up with more noise where you really want to have it. Sorry, that's a very long answer. All right, we're not totally done, so I've still got a couple minutes and something else to talk about. All right, so there's some room for improvement by taking advantage of higher level knowledge, and I think I said the rest of that. In the remaining few minutes, I want to also show you how to find straight lines in images, which can be a useful ability. So here's the canny edge image for this Monaco palace. And then we want to try to find straight lines in the image. That can be useful for reasoning about geometry or for characterizing the appearance of different regions. So first we run canny, and then we get the strength of the edges and their orientations. Then assign the edges to 1 of 8 directions, so 1 of 8 orientations. And then find connected components of edge pixels that are in a particular orientation in one of the neighboring orientations. So I find a connected component for all the edges that have some small range of orientations. And then for each edge, so now I've got, if I look at this image, I'll have grouped, like this whole line will be grouped into one component. And it will be disconnected at this edge here because there's a lot of curvature. So I'll get like a line for the a connected component for the top part of this and a connected component for the bottom. But there'll also be some connected components that correspond to like this curved region. So I want to then throw out the curved regions. So I can compute the straightness of the edge using the second moment matrix, which is something that we'll describe in more detail later. But it's just a measure of how much variance there is in different directions. And if all your variance is in one direction, then it means that you've got a straight edge. If you've got a lot of variance in 2 directions, then you've got a curved edge. So you look at the ratio of the eigenvalues of that second moment matrix. The math is here, but since there's not a ton of time, I won't go through the math. It's pretty simple math anyway when you look at it later. So we compute the second moment matrix. We have a simple test to say if the edge is straight or not, and then throw out the edges that are not straight enough. So this is the result. So here you can see that like we get, as a result, all the edges that are straight. We get these nice straight segments. And edges that are curved just are discarded. And so one thing we could do with this, for example, is estimate the orientation of this surface by looking at where the horizontal-ish edges converge and where the vertical edges converge in the image plane. We'll get to that when we talk about perspective geometry. So I also want to mention homework 1. Let me just... So now you have everything, you should have everything that you need to do homework 1. And so lighting, blah, blah, image pyramid. So it sort of says in the beginning, but I've gotten some questions about what you're allowed to use and not use. The general rule of thumb is that if you can solve a homework problem in 1 line of MATLAB, then you shouldn't use it. So like it's fine to use F-special to create your Gaussian filter, but there's like an image toolbox which I think contains pyramids. So using the pyramid function in the image toolbox kind of defeats the point of doing that problem. So you have some, it's usually somewhat common sense, but you can always ask if you're not sure about a particular function. The part that will take the most time is the edge detection. So here you create an edge detector using just gradient magnitude, and then using oriented gradient filters. And then finally, you describe some ideas for improvement and optionally implement it. We also have a leaderboard, so you can submit the results of your edge detector here and compare results and say a little bit about how you got your results. So if you're able to get a significant improvement, then you can post your result there, and then we can look at the ideas that produce the best results at the end. So I make sure, I'm suggesting that you do this fairly quickly and then start on homework 2, which will be released soon. because homework 2, like the first half of it is creating a feature tracker, which by itself will take you more time than homework 1. And then you'll do shape alignment and then object instance recognition. So as we get deeper into the course, some things get a bit more challenging than so far, even though it might already be challenging. All right, thanks.